For the delay. So we will start our class. Is the screen visible?
Yes, ma'am.
Yes, ma'am. Okay. Actually, I was trying to show it from another device. So for that reason, it's taken some time. So basically, the first thing is that is within this vacation, have you done all the shear force bending moment diagram assignments?
Yes, ma'am.
Yes, ma'am. So, okay. Now, the thing is that this is also will tell in the class. That is, we have to take one class test. Okay. And that class test we have thought of taken at on 20th November. Okay. 20th November is Saturday. And both the laterals students and you, so all of you will have to give the class test. And for
Online
my
mode.
yes, online mode. And for the my part, the syllabus will be up to shear force bending moment diagram. Okay, so I will take out of 15 marks, and this sir will take out of 15 marks or 30 marks. That detail we will tell you later on. But on 20th, me and this sir both will take your class test, and all the number and the timing and how you will give the test. All thing will be discussed, will be given to you. Okay, and you just ask today this sir about his part of syllabus. Now, today we will start principle of superposition. Now, in the previous classes, what we have done all the basic things. That is, what is the property of the materials, Young's modulus, and then the shear force and bending moment diagram for a determinate structure. Now, here we will apply. So this is the case to find the deflection or total elongation using principle of superposition. Now here, the principle of superposition states that on a linear elastic structure, so linear means that is when the stress and strain are proportional, and elastic structure means that is when we remove the load, the structure will regain its original shape and configuration, that is within the elastic limit. So the combined effect of several loads acting simultaneously is equal to the algebraic sum of the effects of each load acting individually. So algebraic sum of effects of each load acting individually. So this principle of superposition is very important. Okay. This will help us to find the resultant shear force bending moment diagram also. Whenever there is a combination of different load cases, suppose a beam is subjected to concentrated load as well as uniformly distributed load. So at a particular point, what will be the shear force or bending moment? The shear force or bending moment at that particular point will be the summation of the shear force caused by the concentrated load plus the shear force caused by the uniformly distributed load. So that is basically based on principle of superposition, and again it assumes this case, that is for the linear elastic structure, that is within elastic limit, we can apply this principle of superposition. Now this is a very simple case. Suppose this is a rod is taken, and here one 8 kilonewton load is applied at the left end, the axial tensile load, and a 4 kilonewton load is applied at the right end. Okay, and in between this, a 4 kilonewton load is applied, the axial load is applied at point B, 2 kilonewton load is applied at point C in the right direction, and in the left direction 2 kilonewton load is applied at point D. And each of AB part, BC part, CD part and DE part length is given. Now we have to find total elongation of this structure. Now how to get that? To get the total elongation, we have to first draw the free body diagram. A second. So first we have to draw the free body diagram. Now to draw this free body diagram, how we can do this? So suppose first we will take this AB part. So for this AB part, at the left side 8 kilonewton load, at the left side 8 kilonewton load. So obviously to maintain equilibrium at the right side also there will be 8 kilonewton load. So that means AB part will be under an axial load of 8 kilonewton. Now come for the BC part. Now in the BC part, so here it is 8 kilonewton. So obviously here to maintain equilibrium here will be 8 kilonewton. And already there is 4 kilonewton right direction load is present. So left direction 8 kilonewton, right direction 4 kilonewton. So the net load is 4 kilonewton left direction. So the part BC is subjected to an axial load of 4 kilonewton in the left direction. So obviously again to maintain equilibrium at the side C, the load will be the opposite side 4 kilonewton. Now as here it is 4 kilonewton right side, so again when we consider the CD part, in the CD part here it is 4 in this direction and 2 in this direction. So the net load is 2 kilonewton at the left direction. So obviously again to maintain equilibrium at point D, there will be 2 kilonewton in the right direction, equal and opposite force to maintain equilibrium. And the part DE, the part DE, you see at, if we get a 2 here in the right direction, so obviously there will be 2 here in the left direction, and again 2 already present in the left direction, this one. So net 4 in the left direction, and at the right side 4 kilonewton right direction. So it is already given. So that means the free body diagram is okay. So now we can say that part AB is subjected to a load P1. P1 is 8 kilonewton. The load, the member BC, the part BC is subjected to a tensile load of 4 kilonewton. Part CD is subjected to a tensile load of 2 kilonewton. And part DE is subjected to a tensile load of 4 kilonewton. And each one is having different length. So the cross section may also be different. We can provide different cross section. The materials can also be different. So we can have E1, E2, E3, E4. So if for this particular case, if the cross section area and E value is taken as same, That is A1 equal to A2 equal to A3 equal to A4 is equal to 225 millimeters square. And similarly, if the modulus of elasticity is same, if we consider the same material, then the E value will be 200 GPa. So we can find out the total elongation. So here I have written do yourself. That means you have to do this problem. Just put the value of P1, L1, P2, L2, P3, L3, P4, L4, and all AE will be same, and you will get the total elongation capital D here. Is this okay?
Yes, ma'am.
Yes, ma'am.
So now,
Yes,
in the
ma'am.
next example, if we see, so if we have the bars of varying cross section, okay, suppose the first part, the diameter is D1, small d1. This for the second part, the diameter is small d2. For the third part, the diameter is small d3. And all the lengths are also different. Then the extension of bar will be using the principle of superposition. The extension of bar will be the extension of this L1 part, then plus extension of this L2 part, and plus the extension of this L3 part. So total extension will be summation of all these extensions. So now again, if you draw the free body diagram here, you will see. So for this case, if you draw the free body diagram, so this is the free body diagram of the first part. Okay, because the left part is subjected to the load P1. Second. No, that is a separate case. So for this case, so if this is P1, so obviously here will be P1. So the first part is subjected to a load P. Okay. So again, for the second part also, P will be here and P will be here. So because these loads, all these loads are axial, so here all the members will be subjected to the same axial load. And there is basically no load is acting in between. So all the members are subjected to the axial tensile load of P. So what will be the total elongation? So this will be PL by AE. So P and E is having same value for all the parts, and L1, L2, L3, these are different for these three parts, and A1, A2, A3, these are different for these three parts. So we can get the total elongation for this particular bar of varying cross section. So in the previous case, we have seen the having same cross section area but subjected to different axial load. Here we have seen subjected to same axial load but different cross section. Now this is another case where it is subjected to various cross section and also various load here, axial load. So here at the left end, axial load is P1. So here at the right end, the axial load is P4. So again, in this cross section, the axial load is P3 in the left direction. And here at this end, the axial load is P2 in the left direction. So for this case, if we draw the free body diagram as, so suppose this is part 1, this is part 2, this is part 3. So suppose for part 1, so P1 at the left side, P1 is the axial load applied, tensile load. So obviously to maintain equilibrium, at the right side, P1 will be applied in the opposite direction. So the first part is subjected to a tensile load of P1. Okay. So now if we draw the free body diagram of second part of L2 length, what will be the load there? Okay, so I have drawn here the left part first and the right part. For the right part, you see here the P2 at the right side, P2 is applied. That is a compressive load, axial compressive load. P2 is applied here. So obviously, to maintain equilibrium at the left side, a P2 compressive load will act along the same axis in the opposite direction. So the last part is subjected to a compressive load of P2. Okay. Now come to the middle part. So in the middle part, if you take the left side, you see, so here at the left side, that is for the member 1, a P1 in the right direction is applied. So obviously here there will be a P1 load to maintain equilibrium, and already a P4 load is applied here, P4. So the net load at this end will be P4 minus P1 in this direction, that is in the right direction. If we take this direction in the right direction, then the load value will be P4 minus P1. Now, suppose if P4 is less than P1, then it will be negative, and in that case, it will be subjected to, it will be actually tensile. The direction will change only. Okay, and if we take the right side, so here, for this member 3, here it is a compressive load of P2, here is acting. So obviously here, a P2 load will come at this end in this direction, in the left direction. P2 will come in the left direction, and already here a P3 load is already acting in the left direction. So with P2, there is another load is acting, P3 in the left direction. So the total load will be P2 minus P3, which is acting in this direction. Okay, so from this free body diagram of the second part, we can say P4 minus P1 must be equal to P2 plus P3. Now suppose, for example, if for your case it is given, suppose P1, P2, P3 given. So in that case, you have to find P4 using this formula, using this equation, because to maintain equilibrium, P4 minus P1 must be equal to P2 plus P3. So from this equation, you can find the unknown one, and then you can calculate the net deformation. So the deformation for this part 1 will be tensile. So as the load is tensile, so it will elongate. So there is plus. For the second part, it is compressive load. So it will be minus. That is, it will be, the length will decrease. And for the third part, again, it is a compressive load. So there will be again minus. So the length will decrease. So the net elongation will be plus this one, minus this one, and minus this one. Okay, এটা কি বোঝা গেল?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so very simple one. This is actually based on the principle of superposition. Now, come to another case, that is stress in compound bar. If the bar is compound in nature, compound means suppose the bar is made up of 2 or 3 types of material. So here, the bar is made up of two types of materials. So it is actually joined here. So it is basically joined here in such a way, with such strong glue type thing, such that it will behave monolithically. It will behave monolithically. That means it will extend, or there will be extension or contraction, but both will be monolithically. There will not be any slip here along this joining portion. So if the bars is behaving monolithically, then what will happen? The thing is that the strain produced in two bars will be same. That is, suppose for this load P, it will elongate like this. So the strain will be same for this bar 1 and this. Suppose this is of material 2. So for material 1 and material 2, both cases, the strain will be same. So strain same means sigma 1 by E1 is equal to sigma 2 by E2. Sigma 1 is the stress produced in material 1 and sigma 2 is the stress produced in material 2. So this is the main thing. Whenever there is a compound bar, whenever there is a composite section, there the strain must be same. That means it means that the bar will behave monolithically. Okay. Now this load P is shared by two materials, and the force taken by this member 1 will be suppose P1, and the force taken by this member 2 is suppose P2. Member 2 means material 2. Now for the stress equation, P1 I can say sigma 1 A1 and P2 is sigma 2 A2, and the total load P will be P1 plus P2. So this equation we can write. Okay, so we are having these two equations. P is equal to sigma 1 A1 plus sigma 2 A2, and another thing is this equation, that is the strain is same. So using these two equations, we can find the forces produced in individual material and what will be the strain, what will be the stress, all these things we can find out, because for these cases, A1, A2, all these are known to us. Okay. So this is the case for stress in compound bar. So a compound bar stress ta bochha gelo ki?
Yes, ma'am.
Yes, ma'am.
Okay. Now this thing will be utilized in case of finding the thermal stresses later on. So first come to the thermal stress. Now this thermal stress is very important part in designing. So you have heard that for the rail line, okay, after a certain distance, a gap is provided. Why? So the gap may be 4 millimeter, 5 millimeter. Okay, suppose after 40 meter length, a gap is provided. The rail line is not continuous. Similarly, for long structures, a gap is provided there. Suppose a long building structure, after a specified length, there will be a gap. That means two buildings are not connected. So why this gap is provided? Such that it can take care of the thermal stress. That means whenever temperature will rise or fall, that is whenever there is a change in temperature, there will be elongation or contraction. So it have to get sufficient space for this elongation or contraction. Suppose for this case, I'm talking about this second case. So this is a cantilever bar. Now if we increase the temperature of this cantilever bar, so for this cantilever bar, one end is fixed, another end is free. So if suppose initially it is under temperature capital T. Now after some time, suppose the temperature is increased to capital T plus delta T. So whenever there is a change in temperature, obviously there is a change in length that is there will be elongation. So the formula of elongation we already know, that is delta L is equal to L alpha delta T. So this is the expansion or contraction. Now if this is the free end, whether any stress is will come here? No. That means if it is getting sufficient space for elongation, then no stress will come in between. So no stress will come in the material because it is getting that space. So in the rail line, if that 4 or 5 millimeter gap is provided between two long lines, then whenever temperature rises, so it will increase its length such that the stress cannot be produced inside. Because in that case, the material have to take extra stress, thermal stress. We want to reduce the stress. So L alpha T, so it will try to elongate and it is getting that space for elongation. But, so there is no thermal stress. But if we just try to restrain that end, if we try to restrict this movement by providing a support here, that means this support is basically providing an opposite direction force such that no elongation occurs. So in that case, a stress is provided here. A thermal stress is provided here. Okay. So whenever we are providing a support here to restrain the elongation, so that means this support is providing a force which is creating a strain of delta L by L, where capital L is the original length, delta L is the extension which it is trying to prevent. Okay. So delta L by L. So from this we can say delta L by L is alpha into delta T. So this strain is produced here. So the stress is modulus of elasticity into strain. So that means E into alpha delta T. So E alpha delta T. So this is the stress produced inside for this case, for this third case. So you can see that the stress produced here, it is independent of the length of the member. It is independent of the length of the member. It just depends on the modulus of elasticity, coefficient of expansion, and change in temperature. Okay. So that means whenever a member is free to expand due to temperature, then no stress is produced there. But if no thermal stress is produced there, but if it is restrained by providing some support like thing, then a thermal stress is provided. Now suppose if this support is basically given here such that it will not prevent this whole delta L, but it will prevent up to something, suppose a small delta. So this support will not prevent the full length delta L. It will prevent a small length, suppose delta. Okay. So that means in that case, okay, if a rod when solid rises temperature, it is permitted to extend only by delta. Okay, no, not this is delta, sorry. The delta is this part. So, suppose the support is provided in such a way so that it will prevent the movement up to this, such that the member of original length, now there will be extension of delta only. It is permitted to extend only by delta. So that means this support, what is the amount of length it is preventing? So the amount of length is L alpha T minus delta. So L alpha T, This is the total length, that is delta L minus delta. So this is the length it is preventing. So the thermal stress will be produced for this length only, the length up to which it is preventing. So if this is the length it is preventing, so what will be the strain then? Temperature strain. So this will be the change in length divided by original length, that is capital L, and the temperature stress will be modulus of elasticity multiplied by the strain. Okay, so this is the temperature stress produced, and again you see it is trying to elongate, but the support is providing a compressive force here, so that it cannot elongate to such a manner. So that means a compressive stress is produced inside the material. So that means whenever a member is trying to elongate and someone from outside is trying to squeeze that, so that means a compressive stress is produced inside. Okay, so this is the compressive thermal stress, it is coming here. এটা কি বোঝা গেল?
Yes, ma'am.
So a very simple problem, I have taken this from the book. A rod of steel is 20 meters long at a temperature of 20 degrees centigrade. Find the free expansion of the rod when the temperature is raised to 65 degrees centigrade. Very simple. So 20-meter length, change in temperature is 65 minus 20. So find the temperature stress produced when the expansion of the rod is prevented, when the full expansion of the rod is prevented. And the second is when the rod is permitted to expand by 5.8 millimeter. So first, let us take this case 1, that is when the expansion of the rod is prevented, find the temperature stress. So in the previous case, you see this L is given 20 meter, alpha value is given. Take alpha and E value like this. So alpha and E value, the material property is given. So L you know, alpha you know, delta T you know. So this delta L you know. Delta L you can find out. So after getting this delta L, you can find out this strain. And after getting this strain, you can find out this thermal stress when the full expansion is prevented. And in the second case, when the rod is permitted to expand by 5.8 millimeter. So here it is permitted to extend by 5.8. So this delta value is given 5.8. So then the expansion prevented will be L alpha delta T minus delta divided, and the strain will be the whole thing divided by L, and the temperature stress is E multiplied by that strain. So solution for the first part, the free expansion of the rod is L alpha T small l here, and is the total length, and capital T is the change in length. So 10.8 millimeter is the free expansion of the rod. When the expansion is fully prevented, the temperature stress is alpha TE. So you see the temperature stress is alpha TE, this formula. So alpha TE. So after getting alpha and E value, we can find out the temperature stress is 108 Newton per millimeter square. When the rod is permitted to expand by 5.8 millimeter, the expansion prevented is 10.8 minus 5.8, that is 5 millimeter. Then the strain will be this, and the temperature stress will be this, 50 Newton per millimeter square. So you see, if the rod is some amount of expansion is, if it is permitted, then the stress reduced is much more. Okay, so this is a very simple example to show you how the temperature stress is produced here and what will be the type of the stress? Tensile stress or compressive stress?
Ma'am, compressive.
So here, as here the elongation is taking place, so the compressive stress will come. Now, we will combine these cases. Combine these cases means, suppose now our material is a composite type material or compound bar. Okay, so when the compound bar is subjected to temperature stress, then what will happen? So temperature stress in compound bar. Now, suppose this is a bar of made up of two material, material 1 and material 2. Okay, so it is no support is shown at the right side. So you see, when the compound bar is subjected to change in temperature, what will happen basically? Suppose material 1, it will extend up to alpha 1 TL, and the material 2 will extend up to alpha 2 TL. Now this L is this length. So this is L. Okay. So capital T, capital L. Here capital T is the change in temperature. Only alpha 1 and alpha 2 is different. So for this, from this figure, so for this case, we have assumed alpha 1 is greater than alpha 2. We have assumed this. So if alpha 1 is greater than alpha 2, then the elongation of material 1 will be more than elongation of material 2. Okay. Now, as the bar is composite in nature, that means there will be no slip here. That means the bar will behave monolithically. So it will not expand like this. Okay. So material 1 will expand up to alpha 1 TL, material 2 will expand up to alpha 2 TL. It cannot happen. So its net elongation will be like this. Suppose a delta, capital a delta. That is, it will elongate up to XX, suppose, which will be more than alpha 2 TL and less than alpha 1 TL. So there is a bit of compromisation like thing. So the net deformation will be greater than alpha 2 TL but less than alpha 1 TL. Okay. So from the figure you can see that suppose, so this length is suppose delta. So the net elongation is delta. Okay. So for material 1, you say what is the type of stress is produced? Because material 1 is trying to expand up to alpha 1 TL, but the net elongation is delta coming. So that means there is a net squeezing, basically. A net change in length occurs up to this part. And it is basically coming like this. So material 1 is subjected to a compressive stress. Okay. And material 2, its length, if there is no support, if there is no material 1 like thing, then it will increase up to alpha 2 TL. But due to presence of material 1, it is extending more up to delta. So that means again it will increase up to this. So material 2 will be subjected to a tensile stress. So a compressive stress will be produced in material 1 and a tensile stress will be produced in material 2. And there is no external force is applied here. Only the temperature is actually increased. So no external force, mechanical force is acting here. So obviously the compressive force on material 1 must be equal to tensile force on material 2, so that it becomes an equilibrium. Okay. So compressive force in material 1, that means sigma 1 A1 is equal to sigma 2 A2. Sigma is the stress produced in material 1 and sigma 2 is the stress produced in material 2. So obviously this equation comes, and from this we can write this sigma 1 is equal to this. Okay. So the first thing we have seen that the total force must be 0 to maintain equilibrium. So compressive stress on material 1 must be equal to tensile stress on, compressive force in material 1 must be equal to tensile force on material 2. এক second. Hello, sir. Hello. শুনতে পাচ্ছেন? আমি ক্লাসে আছি, আমি একটু পরে আপনাকে রিং ব্যাক করছি। So this is the case that this equation we can use.
Ma'am, in the previous, in 11 and 12, we have learned that if in such cases the bar becomes bent
Yes.
at one end.
Yes.
So why here it is not bending?
Yes, it will bend. A bending stress will come, but here for this thing, if here actually we have provided the axially, we have provided, suppose this is a bar, okay, if we just increase this, because in your cases whenever there is a bend,
Bending is restricted.
Yes,
okay.
Because here you have seen that one part is fixed here. Okay. So
yes.
for this case, it will be straight. But where you have seen the bending part in your 12, I think, so there the both end is free.
Yes, ma'am.
Okay. So this is the stress. Now, as the two bars are connected together, the actual position of the bar will be xx. So it is okay. We know that the actual position will be xx. Now, actual expansion of material 1 must be actual expansion in material 2. That means actual expansion means this is this delta part. Okay. So the initial position is this and the final position is this. So this is the actual expansion delta. So actual expansion delta. So here you see, so this material 1, the strain produced, okay, will be this alpha 1 TL minus delta. This is the change in elongation, which is actually delta DL1, this part. And for material 2, the change in length will be DL2. So alpha 1 TL minus DL1. So you see, alpha 1 TL is the full length minus DL1 is the delta. So here basically this is delta. So this delta we can calculate from material 1 and from material 2. So from material 1, the delta will be alpha 1 TL minus DL1. And for material 2, the delta will be alpha 2 TL plus DL2. So this is the delta. Now here alpha 1 TL. Now this DL1. This DL1 is the change in length that is occurring in material 1. So the strain will be delta DL1 divided by L. No, the thing is that here, one thing. So this, yes, that is the strain. Oh, so if the compressive stress produced in material 1 is sigma 1, if this is the compressive stress produced, then what will be strain? Sigma 1 by E1. This will be the strain in material 1 multiplied by capital L, that is the original length of the material 1. So this is same as DL1. Because the compressive stress produced in material 1 will be due to this prevention of length, this DL1. Similarly for material 2, if the tensile stress produced is sigma 2, divided by E2. This is the strain multiplied by the original length L. This must be equal to DL2. So here, putting this thing here and this capital L, this is cancels out from all the expressions. We get this expression. So from this equation 1, this one, and from this equation 2, we can find out the stresses sigma 1 and sigma 2. What is the stresses that is coming in this materials? So the material 1 is subjected to a thermal stress sigma 1 and material 2 is subjected to a thermal stress of sigma 2, and that we can find out. So what amount of thermal stress is producing in this materials. Now, following the same thing, if we just do one problem here, you see a steel bar is placed between two copper bars. You see the figure. The steel bars is in between this two copper bars having the same area and length as the steel bar at 15 degrees centigrade. Okay. At this stage, they are rigidly connected together at both ends. They are rigidly connected duto endi. When the temperature is raised to 315 degrees centigrade, the length of the bars increased by 1.5 millimeter. So, the total length is bola nei. Total length ta bola nei. So, eta bola ache the length of the bars increased by 1.5 mm. So, ekhane net increase ta bola ache, delta ta bola ache. Determine the original length and the final stresses in the bars. এর অরিজিনাল লেন্থ কত আর এদের মধ্যে ফাইনাল স্ট্রেস কত তৈরি হচ্ছে। মডুলাস অফ ইলাস্টিসিটি অফ স্টিল কংক্রিট আর হচ্ছে কোএফিশিয়েন্ট অফ এক্সপ্যানশন ফর স্টিল অ্যান্ড কংক্রিট এখানে বলা আছে। ওকে, সো এখান থেকে দেখা যাচ্ছে যে কোএফিশিয়েন্ট অফ এক্সপ্যানশন ফর স্টিল ইজ গ্রেটার দ্যান that of is less than that of copper. So steel coefficient of expansion is less than that of copper. So which one will increase more? Copper will increase more. The copper part will increase more than the steel part. So as the copper part will increase more, so what is the type of stress that is coming in the copper and steel?
Ma'am, compressive.
Huh?
Ma'am, copper bar will be under compressive stress and steel bar will be under tensile stress.
Yes. So copper will be under compressive stress, steel will be under tensile stress. So the solution is let the sectional area of the steel component be A millimeter square. Now here for this case, the cross section area, it is only given that each having same area and same length. So the area of all these things are same. So let the area of the steel and copper is A, capital A. So the sectional area of steel component is that is capital A. Now here two copper component, two copper bar. So the sectional area of copper component is 2A. Now free expansion of steel is alpha STL. Free expansion of copper component is alpha CTL. Now let delta be the actual expansion of each bar. So here let delta be the actual expansion which is given, that is 1.5 millimeter. And this delta must be greater than alpha STL and must be less than alpha CTL. So that means steel is in tension and copper is in compression. Now let Fs and Fc So in the previous cases, I have shown it there in terms of sigma 1, sigma 2. So here the stresses is named as Fs and Fc for the steel and copper respectively. Now for the equilibrium of the system, the total tension force in steel must be equal to total compression force in copper. So if the stress produced in steel is Fs, the cross-section area of steel is A, so Fs into A is equal to Fc into twice A. So Fs is equal to 2Fc. So this is equation number 1. Okay. And for the second case, now actual expansion of steel. Now the actual expansion of steel is, the actual expansion is same, that is delta. So this delta for steel is alpha STL, because for steel it is less. So you see, for steel, the free expansion is alpha STL. Okay, but it is expanding up to delta. So this delta is alpha STL plus Fs by Es into L. And considering copper, it is alpha CTL minus Fc by Ec into L. So here this equation is basically equation number 2. So this thing you can see. So I have applied this equation. So from this equation number 1 and equation 2, we are just solving this. Now you see, for all these cases, small l is cancels out. So we are getting this. So here, capital T value, that is the change in temperature 300 degrees centigrade. So here, just putting all the values given, we have got another equation of this. Taking this Fc and Fs. This Fc and Fs, we can get another equation. Just check it. I think it is Fc and it is also Fc. Oh, here this is Fs. So Fs is replaced as 2Fc, because here we have seen that Fs is equal to 2Fc. So we have used this equation here to find out Fc, and then we have got Fs. So this is the stresses produced in copper, and here this is the stress produced in steel. So the actual expansion of the steel bar, we know that the delta is equal to alpha STL plus Fs by ESL. So from this equation, we can find out this small l, that is the length of the bar, 340.526 millimeter. Okay, so here we have seen that in this problem, all the material properties will be known to you for the stress calculation. That means the coefficient of expansion, modulus of elasticity, these things. And the change in temperature will be also known to you. And the total geometry, that is the cross-section area, length of the bars, all this will be known to you. You have to find out the stresses produced. So in this way, we can get the stresses produced in the bar, because these stresses are very important where there is this stress calculation for this thermal stress is very important whenever there is extreme weather. Suppose at the daytime, the temperature is very high, suppose 50 degrees centigrade. But at the night time, the temperature is very less, suppose 10 degree, 5 degrees centigrade. So for that type of extreme weather, this temperature stress calculation is very important, because this temperature stress has to be added with a mechanical stress. The stress is produced due to external load. And then we have to check whether the material is capable of taking that amount of stress or not. That checking is necessary. So this is the thing regarding the thermal stress. So in the next class, we will do other part. Okay, this axial extension under self-weight of bar, strain energy, gradually and suddenly applied load. So all these things we will do in the next class. So up to this, is it okay? Have you understood?
ম্যাম
বলো।
বলছিলাম এই থার্মাল স্ট্রেসের যে স্টার্টিং এ যে আপনি দেখিয়েছিলেন না চারটা ফিগার, ওটাতে 3 নম্বর ফিগারে যে ডেল এর ব্যাপারটা বললেন ওটা বুঝতে পারলাম না। আলফা এল আলফা টি এল মাইনাস ডেল বাই এল যেটা করেছিলেন ওই জায়গাটা একটু বুঝতে
কোন
অসুবিধা
ফিগারটা
হলো।
বলো?
এর আগেরটা এই যে এখানে স্যার ম্যাম 3 নম্বর ফিগারটা 3 নম্বর,
হ্যাঁ
যেখানে আপনি এই যে 3 নম্বর ফিগারটাতে বললেন না ডেল এর ব্যাপারটা, ওই
হ্যাঁ
ডেল এর ব্যাপারটা
ওখানে
বুঝতে পারলাম না।
এক্সপেনশনটা অ্যালাউ করা হচ্ছে।
মানে ম্যাম ফার্স্টে কি তাহলে বারটা কি ফ্রি থাকবে, পরে ওই ফিক্সড এন্ডে গিয়ে লাগবে এক্সপেনশন হয়ে, ডেল এক্সপেনশন হয়ে কি ফিক্সড এন্ডে গিয়ে লাগবে?
না, মানে বেসিক্যালি ব্যাপারটা হচ্ছে যে আমরা এখানে সাপোর্টটা আগে থেকেই প্রোভাইড করব। এখানে হচ্ছে যে সাপোর্ট মানে কেউ যদি তোমাকে প্রিভেন্ট করে, তুমি এক্সটেনশন হতে চাইছো, তোমাকে প্রিভেন্ট করছে, তখন তোমার মধ্যে স্ট্রেস আসছে। এবার ওই প্রিভেনশনের লেন্থটা তোমাকে মানে কোথায় দেবে? হ্যাঁ, মানে মাঝখানে ওখানে একটা গ্যাপ থাকবে আর কি, ঠিক আছে? ওখানে একটা গ্যাপ থেকে ওখানে একটা সাপোর্ট থাকবে, মানে তোমার ওই বারটা ইনক্রিজ হয়ে আপ টু অত অব্দি ইনক্রিজ হতে পারে, তার থেকে বেশি ইনক্রিজ হতে গেলে ওই সাপোর্টটা তোমাকে উল্টো দিক থেকে ধাক্কা দেবে,
হ্যাঁ কম্প্রেশনটা করবে, ওটা
কম্প্রেশনটা তখন করবে,
জেনারেট হবে। হ্যাঁ
জেনারেট হবে।
প্রথমে তো টেনশন জেনারেট হবে, তারপরে কম্প্রেশন জেনারেট হবে যখন ওখানে গিয়ে লাগবে বারটা, তাই তো?
যখন ওখানে লেগে গেল মানে একটা পার্টিকুলার টেম্পারেচার অবধি ও তো ফ্রি এক্সটেন্ড হলো আপ টু দ্যাট সাপোর্ট, এবার তারপরে যখন টেম্পারেচারটা আরো ইনক্রিজ হলো তখন কম্প্রেসিভ স্ট্রেসটা জেনারেট হলো।
আচ্ছা ঠিক আছে, থ্যাংক ইউ।
ম্যাম একটা পার্টিকুলার স্লাইডের পেজে নিয়ে যাবেন, লাইক এটার পরের পেজটা, ওই প্রবলেমে। ইয়েস ম্যাম, এটার পরের পেজটা, ইয়েস ওটাই ব্লু রঙের পেজটা ম্যাম।
এর আগে?
হ্যাঁ ব্লু রং, ইয়েস এটাই জাস্ট একবার। থ্যাংক ইউ ম্যাম, হয়ে গেছে।
ঠিক আছে, I will give you another problem sheet regarding this stress calculation for the composite bar using this principle of superposition, and also the problem sheet on this thermal stress. Okay, 4টে কি 5টা প্রবলেম আছে, তোমরা সেগুলোকে একটু মানে বাড়িতে প্র্যাকটিস করো এক্সামের জন্য। মানে এক্সাম মানে ক্লাস টেস্ট নয়, ক্লাস টেস্ট এগুলো নেই, ক্লাস টেস্টে শিয়ার ফোর্স বেন্ডিং মোমেন্ট ডায়াগ্রামই রয়েছে আপ টু দ্যাট আর কি। মানে প্রথমে যেগুলো পড়ানো হয়েছিল সেগুলো, তারপরে শিয়ার ফোর্স বেন্ডিং মোমেন্ট ডায়াগ্রাম, মানে পুজোর আগে যা যা হয়েছে সেগুলো সব। ওকে, সো আজ থেকে যেটা হচ্ছে সেগুলো তোমাদের ক্লাস টেস্টে থাকবে না, বাট নেক্সট ডে তোমাদের সেমিস্টার টেস্টে এগুলো সব আসবে। সো তোমরা সেইভাবে প্রিপারেশন নিও, প্র্যাকটিস করো, প্র্যাকটিস শিট আর এই কটা স্লাইডের আমি তোমাদের পাঠিয়ে দেব। আর আমি তোমাদের নেক্সট ক্লাস নেব মঙ্গলবার দিন, ঠিক আছে? তো মঙ্গলবার দিন আবার ওই 9টা বা 9:30 থেকে সেটা আমি জানিয়ে দেব। টিউসডেতে আমি তোমাদের ছোট করে একটা ক্লাস নেব।
ম্যাম সেমিস্টার এক্সাম কেমন ডেটে হতে পারে, কোনো আইডিয়া আছে?
আমার কোনো আইডিয়া নেই গো, তোমাদের তো এক্সাম তো মানে তোমাদের তো সেশনই ডিসলভ করছে ডিসেম্বরের মাঝখানে বা ফার্স্ট সেকেন্ড উইকে মেবি। তো তারপরে তো তোমাদের তো একাডেমিক ক্যালেন্ডার তোমাদের কাছে আছে না?
ম্যাম আছে, বাট ওটাতে তো বলা ছিল না যে আমাদের 25 to 31 এর মধ্যে ওই মিড সেমটা হবে, বাট মিড সেমটা হলো না।
তোমাদের মিড সেম হলো না, তার একটাই কারণ, যেহেতু ল্যাটারাল স্টুডেন্টরা জয়েন করেছে, তো ল্যাটারালরা তো জাস্ট পুজোর আগে জয়েন করেছে, ল্যাটারাল স্টুডেন্টদের কথা ভেবেই তোমাদের এই সময়টা হলো না। কারণ ওদের তো একটু প্রিপারেশনের সময় দিতে হবে সেই কথা ভেবে, কারণ তোমাদের আমরা আগে পরীক্ষা নিয়ে নেবো, ল্যাটারাল স্টুডেন্টদের আবার পরে আলাদা করে নেব, সেটা একটু অসুবিধাজনক, ঠিক আছে? সেই জন্যই থার্ড ফোর্থ ইয়ারের সব পরীক্ষাগুলো 25 থেকে 30 উইকের মধ্যে হয়ে গেছে। খালি তোমাদের জন্য পরীক্ষাটা আমরা নভেম্বরের মধ্যে নেব, এটাকে আমরা ঠিক করেছি আর কি। সো তোমাদের বাকি সব সাবজেক্টেরই এক্সাম নভেম্বরের মধ্যেই হবে ক্লাস টেস্ট, যাতে ল্যাটারালরাও একসঙ্গে পার্টিসিপেট করতে পারে। ঠিক
ঠিক
আছে,
আছে ম্যাম।
সো ঠিক আছে, তাহলে তোমাদের 20 তারিখে হবে এক্সাম ক্লাস টেস্টটা, তার ডিটেল তোমরা পেয়ে যাবে। সো ওকে, আর তোমরা সমস্ত নেম রোল নাম্বার তোমরা এ করে লিখেছো তো চ্যাট বক্সে?
ইয়েস ম্যাম। আর ম্যাম ওই
Yes, ma'am.
চিঠিটা কি 15 নাগাদ করার চান্স আছে ম্যাম?
কি কি
ক্লাস টেস্টটা আপনি তো বলছেন পুজোর আগে অবধি রাখছেন সিলেবাসটা,
হ্যাঁ,
তাহলে ওটা ম্যাম?
অনলাইন আছে, অনলাইনই হবে।
আচ্ছা আচ্ছা
ক্লাস টেস্ট অনলাইনেই হবে তোমাদের।
আচ্ছা আচ্ছা, ঠিক আছে।
ঠিক আছে, ওকে, ঠিক আছে, তাহলে এন্ড করছি।
ওকে ম্যাম।
ওকে, তোমরা লিভ করো।